Thus far, most of the reactions we've encountered occur in just one direction, that is, the conversion of reactants into products. However, reactions can go in the opposite direction too, that is, products undergo reaction to reform reactants. In fact, most reactions go in two directions. Over time, the typical chemical reaction appears to stop, and both reactants and products are present. This point is known as chemical equilibrium. For example, the reactant dinitrogen tetroxide N2O4 undergoes a decomposition reaction to give the product nitrogen dioxide NO2. This is known as the forward reaction. Once produced, NO2 molecules undergo a dimerization reaction, that is, pairs of NO2 molecules recombine chemically to form N2O4 molecules. This is known as the backward or reverse reaction. This reaction that goes in both directions is known as a reversible reaction. In a chemical equation such as the one shown in the example, when a double arrow symbol is used, it means that the reaction is a reversible reaction and that reactants and products are at equilibrium. Let's take a closer look at the idea of chemical equilibrium. Dinitrogen tetroxide is a colorless gas, while nitrogen dioxide is a brown gas. In a particular reaction, dinitrogen tetroxide is first placed in an empty transparent reaction vessel. The vessel is then sealed. Sealing the vessel is important. If not, the gas escapes and air enters the vessel. In such a case, the reaction cannot reach equilibrium. For equilibrium to be achieved, the chemicals in the system must be in a sealed enclosure. Such a system is called a closed system. Over time, the reaction mixture turns from colorless to light brown to a darker shade of brown. This signals the formation of nitrogen dioxide. There comes a point in time when the mixture's shade of brown no longer changes. That is, its intensity is maintained. This gradual change is represented by 5 snapshots of the contents of the reaction vessel over time, as well as what happens at the molecular level. These correspond to points on 2 graphs. One is the concentration of dinitrogen tetroxide against time graph. The other is a concentration of nitrogen dioxide against time graph. Let's take a closer look at the graphs, starting with the N2O4 graph. At the start, when time is equal to 0 minutes, there is plenty of N2O4, so the concentration of N2O4 is high. This is denoted by the point of the N2O4 graph touching the top of the vertical concentration axis. Since its concentration is high, it is more likely to collide with the reaction vessel wall and with each other to undergo decomposition. Its rate is therefore fastest at the very start. This is shown by the steep slope of its graph at this point. As time passes, the slope becomes less steep as concentration of N2O4 decreases, so rate decreases, and this is represented by the gentler slope. Eventually, the graph plateaus, that is, it levels and becomes horizontal, or at least approximately so. From this point forth, the concentration of N2O4 no longer changes and becomes constant. Now for the NO2 graph. This graph starts off with a 0 concentration of NO2 at time 0. Its slope is steep at first, since the high concentration of N2O4 allows for more effective collisions to produce NO2 quickly. Over time, the production of NO2 slows down as the decreasing concentration of N2O4 gives rise to fewer effective collisions. Rate therefore decreases, and this is shown by the gentler slope. After some time, this graph also plateaus, that is, it is now horizontal. The concentration of NO2 no longer changes and becomes constant. When the concentration of reactant N2O4 and that of product NO2 no longer change, that is, when the mixture takes on an unchanging shade of brown, N2O4 and NO2 have reached dynamic equilibrium. When the reactant and product achieve equilibrium, their concentrations don't change anymore. In addition, the rate of the forward reaction is equal to the rate of backward or reverse reaction. At equilibrium, though the concentrations of N2O4 and NO2 are constant, their equilibrium concentrations are different, as can be seen from their graphs. The constant values are different. Notice that the constant concentrations are not 0, 2. Now, just because the reactant and product concentrations no longer change, does it mean that reaction has stopped? Well, it might appear to have stopped, but it hasn't really. The word dynamic in dynamic equilibrium means that the reaction is still happening. In other words, the two-way reaction is happening all the time. N2O4 is busy decomposing into NO2, and NO2 is busy recombining into N2O4 simultaneously at the same rates. Perhaps a little analogy might help. Suppose there is a popular food court stall selling yummy soups that has perpetually long queues. At noon, while you are seated at a table having lunch, you notice that there are 20 people lining up to place their orders. At 12:30, after finishing your meal, you notice that there are still 20 people in line. What is going on? Has the queue not moved at all? It has. It turns out that each time a person leaves the queue after payment, a newcomer joins the queue. Though there is a constant number of 20 people waiting to place their orders, the queue is moving. It only appears to not be moving.